Okay, let's talk about that specific kind of dread you feel when you have to present a model to a stakeholder.
Oh, I know this feeling.
You've done all the work, right? You've cleaned the data, you've tuned everything, you've validated it, you know the model is solid,
Hmm.
but then you walk into that room or get on that call with, like, the VP of operations, and they just don't care about your cool architecture. They ask that one question.
Is this thing actually any good?
Exactly. And it's somehow the simplest and the hardest question to answer.
It really is. It's that moment where, data science just crashes right into business reality.
Mm-hmm.
Because good, what does good even mean?
Right.
To us, good might be a low-loss function. To the VP, good means, does this save me money or does this make me look stupid?
And you can't just hand them a CSV with 10,000 rows of errors and say, here, you figure it out. You need one number, a single digestible number for the slide.
Which is where we get into the weeds today. We're unpacking the big three error metrics, MAE, MSE, and RMSE.
And I'm glad we are, because I think a lot of us, even people who've been doing this for a while, we just take the default, you know?
Right, whatever scikit-learn spits out.
Yeah.
But choosing between them, it's not really a math decision. It's a business decision. It's a risk management decision.
Okay, I want to jump right into that. But first, let's just clear away the most common trap. The simple average.
Ugh, yes. The mean error.
It seems so intuitive. I have errors of plus 5,000 and minus 5,000. I average them. I get 0.
And you tell your boss, on average, we're perfect. Which is technically true and completely useless.
Right.
It's the old head in the oven, feet in the freezer problem.
Oh.
On average, you're comfortable, but in reality, you're dead.
I haven't heard that one, but it's perfect.
It's a classic. But seriously, positive and negative errors cancel out. It makes a totally chaotic model look stable. So for anyone listening, if you are using simple average as your main KPI, please stop. You need to measure the magnitude.
Okay, so magnitude. That brings us to our first real contender and probably the most human of the metrics. I mean, absolute error, MAE.
I like to call it the fair metric.
A fair metric. Why fair?
Well, because it treats every single error equally. MAE it takes the absolute value of all your errors and then averages them.
So it just strips away the direction. It doesn't care if you were over or under.
Exactly. It only cares about the distance. A 10-point miss is a 10. A 5-point miss is a 5. Simple as that.
Which feels right. I mean, a 10-point miss should be twice as bad as a 5-point miss.
In terms of sheer volume, yes. And this is why stakeholders love MAE. It is so interpretable.
Because it's in the same units as the data.
It's in the same units. If you're predicting house prices in dollars, your MAE is in dollars. You can walk into that meeting and say, on average, our predictions are off by $5,000. Done. No translation needed.
Okay, so it's the accountant's metric. It just sums up the ledger. But I have to push back on this fairness idea.
Go for it.
Is a 10-point miss in the real world really just twice as bad as a 5-point miss? Or does the pain scale, differently?
That is the million-dollar question. And that's where MAE sort of falls short. It assumes the cost of being wrong is linear.
But it's often not.
It's often not. In so many systems engineering, finance, medicine errors don't scale linearly. They scale exponentially.
Give me an example where fair is actually dangerous.
Supply chain. Let's say you underpredict demand by 5 units. Okay, you miss a few sales? Annoying.
Manageable.
But if you underpredict by 50 units, you don't just lose 10 times the sales. You might cause a stockout that shuts down a whole production line.
Right, you're paying for emergency air freight, you're damaging your relationship with a huge retailer.
The cost just exploded. It wasn't 10 times worse, it was 100 times worse. And MAE is too lenient. It doesn't see that.
It doesn't scream fire.
Exactly. It can't tell the difference between 1,000 small cuts and one fatal blow. And that brings us to the strict metric. MSE, mean squared error.
The outlier hunter.
The outlier hunter, for sure. Mathematically, all we're doing is squaring the errors before we average them. But the implication of squaring is huge.
It's all about adding weight. Disproportionate weight.
Disproportionate punishment is how I think of it. An error of 5. The penalty is 25. An error of 10.
The penalty is 100. So you doubled the error, but you quadrupled the penalty.
Exactly. And if you have one massive outlier, say an error of 100, its penalty becomes 10,000.
It just completely dominates the entire calculation.
It does. And from a machine learning training perspective, that's often what you want. You want the algorithm to panic when it sees a huge error and work desperately to fix that one thing.
Because the gradient is steeper, it gives the model a much stronger signal.
A very strong signal. Fix this big mistake first. But And this is a massive but. There is a huge usability problem with MSE.
The units.
The units are total garbage for humans,
If you're predicting house prices, your MSE is in dollars squared.
which means nothing. Good news, boss, our error is down to 4 million square dollars. You get laughed out of the room.
Yeah.
It totally breaks the narrative.
Yeah.
You can't tell a story with squared units. It's a metric for the machine, not for the boardroom.
So on one hand, we have MAE, great for storytelling, but maybe a little too relaxed about risk. And on the other, we have MSE. It's great at flagging risk, but it speaks a language nobody understands. So naturally, we needed a compromise.
And we got one. RMSE. Root mean squared error.
The bridge between worlds. You take that crazy MSE number, you hit it with the square root, and
And you're back in the original units. Dollars, degrees, whatever.
but, and this is the key part I think people miss, you haven't erased the penalty from the squaring step.
You haven't washed away the sin, as I like to say.
Unpack that. Because I think it's easy to assume that since the units are normal again, it's just another kind of average.
It looks like an average.
Yeah.
But it's an average that's been weighted by your biggest mistakes. Let's use that sales forecast example from the source material. This is perfect.
Okay, the week 6 anomaly.
Right. So imagine you're forecasting weekly sales. For 10 weeks, your model is great. It's off by maybe 10 units, 20 units, very tight.
And then week 6 happens, Black Friday, a data feed breaks, whatever. Actual sales are 1,000, and the model predicted 200, a huge 800-unit miss.
Now, if you just calculate the MAE for the whole quarter, that one bad week gets, averaged in with all the good weeks.
It gets diluted.
Totally diluted. The MAE might come out to, say, 80 units, and you report we're off by plus or minus 80, and that sounds acceptable.
But if you calculate RMSE,
You calculate RMSE, that 800-unit error gets squared first. It becomes 640,000. It just blows up the calculation.
so even when you take the square root,
It leaves a huge scar. Your RMSE might be, 250 or 300.
so now you're looking at an MAE of 80 and an RMSE of 300.
And that gap between them, that's the smoke signal. That's the metric telling you, hey, on average, your performance is okay, but you have a volatility problem. You have outliers that are potentially catastrophic.
So if MAE and RMSE are close together, your errors are consistent. If they're far apart, you've got some big sporadic screw-up.
You've got it. And that is why I always tell people, never, ever report just one. The relationship between the two metrics tells a much richer story.
Okay, let's pivot this to decision-making. We have the tools. When do we use which one? You said it's about risk management.
Context is absolutely king.
All right, let's do a scenario. We're running a pizza delivery service. Promise delivery in 30 minutes.
A classic logistics problem.
If my driver is 5 minutes late, maybe I give the customer a $2 credit. If they're 10 minutes late, I give them a $4 credit.
And that's the key right there. The cost of your error is linear.
Right. Being 10 minutes late is just twice as expensive as being 5 minutes late.
One pizza being 45 minutes late is annoying. You lose the cost of that one pizza, but it doesn't bankrupt the company. So in this world, outliers don't break the whole system.
So if I optimize for RMSE here,
You might actually make things worse. Because RMSE is obsessed with preventing that one 45-minute delivery. To do that, the model might create routes that make everybody else's delivery 2 minutes slower.
you sacrifice the average experience to save the outlier.
Yes, for a high-volume, low-margin business like pizza, you want the best average performance. You're on Team MAE.
You want the whole fleet to run smoothly, and you just eat the cost of the occasional mistake.
Exactly. MAE aligns with your profit and loss.
Okay, now let's flip it completely. Scenario B. We're predicting medication dosages for a smart 5E pump in a hospital.
Oh yeah, a totally different beast.
If the model is off by 0.1 milligrams, that's fine, it's just noise.
But if it's off by 10 milligrams,
You could kill the patient.
and that is the definition of a nonlinear cost function. The cost doesn't just go up. It hits a vertical wall. You absolutely cannot afford a single large error.
So if I used MAE here, I'd be criminally negligent.
You would be. MAE would say, hey, we got 1,000 doses right, and we only killed 3 people. On average, our error is microscopic.
That's a dark way to put it, but I get the point.
It's grim, but it's the math. For any safety-critical system structural engineering, autonomous cars, you have to use RMSE. You need the metric that screams at you. You are optimizing for safety, not average efficiency.
What about a gray area, like a customer churn prediction?
Ooh, that's a great one, because it really depends. Who are your customers? If you're a service like Netflix where every customer pays $15.
Losing one isn't a catastrophe. It's a volume game.
Exactly. MAE is probably fine. You just want to capture the general trend.
But if you're an enterprise software company selling million-dollar contracts,
Then losing one of those customers because your model missed them, that's a quarterly revenue disaster. That is an RMSE scenario all day long. You have to be sensitive to those big misses.
So a good rule of thumb is look at the consequence of your worst-case error. If it's annoying, lean towards MAE. If it's catastrophic, you have to use RMSE.
That's a very, very solid heuristic.
I want to wrap up with something that really caught my eye in the source material's conclusion. It's this idea of the ROI of accuracy.
Oh, this is my favorite soapbox.
We spend all this time trying to shave points off our error.
Yeah.
We celebrate when RMSE drops from 3.8 to 3.7, but there's a cost to that.
A massive cost. It's the law of diminishing returns, right?
Yeah.
Getting a model from terrible to okay is usually pretty easy.
Right.
Okay, to good takes more work, but getting from good to state-of-the-art, I mean, that can take months of engineering time, expensive new data, huge compute costs.
And the question is, does the business actually get any value from that last little improvement?
Exactly. Go back to the pizza example. If you spend 3 months and $50,000 to improve your delivery time prediction by 30 seconds, does that actually result in fewer customer refunds?
Probably not. The customer doesn't even notice.
So you just spent a ton of money to improve a number on a dashboard that has zero impact on the bottom line. You improve the math, but not the business.
That is such a common trap for data teams. We get addicted to the leaderboard.
We call it soda chasing the state of the art. The best data scientists I know aren't the ones who can squeeze the last tiny fraction out of an RMSE. They're the ones who know when to stop and say, this is good enough to solve the problem, let's ship it.
So good enough isn't being lazy, it's being strategic.
It's being efficient.
Right.
Look, sometimes a model with a slightly higher error is actually better if it's simpler, faster, and easier to explain to that VP of operations we started with.
So to recap our deep dive today, you start with the FAIR metric, MAE, for interpretability, and when your costs are linear.
Then you use the strict metric, RMSE, when you absolutely need to penalize those big, costly outliers.
And you always, always calculate both.
Watch the gap. The story is in the gap between them.
And finally, don't forget to ask yourself if squeezing out that extra point of accuracy is actually worth the price.
Couldn't have said it better myself.
Yeah.
The best metric isn't a math decision, it's a business decision.
That wraps up our deep dive. Hopefully, the next time you're looking at a list of model errors, you'll know exactly which story you need to tell. Thanks for listening.
See you next time.